This video is design project of image and video processing which was given to us under the mentorship of Dr. Jignesh Patel. In this video, we are going to explain what is JPEG, what are the underlying principles behind it, and how we have implemented it.
Let's start with the introduction. The basic idea behind the image compression process is reducing the size of an image file without significantly compromising its visual quality. This is done to save storage space, speed up transmission over a network, or improve the efficiency of an image processing. So, image compression is the process that makes images file smaller, and image compression most often works either by removing bits of information and redundant information that is including in the image by using an image compression algorithm to rewrite the image file in a way that takes up a less storage space. Let's move on the further slide. Why is image compression important? As we know that compressed image load faster than uncompressed image. This matter because the speed at which web pages application load has a huge impact on search engine optimization, conversion rate, and user digital experience. We can achieve a compression by removing the basic redundancy in the image data like interpixel redundancy, coding redundancy, and psycho-visual redundancy. So the principle behind the image compression and process involves our compression principle is image compression is a process of reducing the size of image file. Then one principle is redundancy removal. Image often contain repetitive and redundant data that can be removed without affecting the visual quality. And second one is irrelevance removal. Image also contain data that is not visual important and can be removed without affecting the overall quality. This can be achieved through a technique such as quantization and entropy coding. Classification of compression. Compression is classified categories lossy and lossless compression. Lossless compression. In a lossless compression, the goal is to reduce the file size without any loss of information. This means that when compressed image is decompressed, it is identical to the original image. It means that we can retrieve as original image same as after compression. And lossy compression on other hand allows for a same loss of data in order to achieve higher compression ratio. The idea is to remove a non-essential information that the human eye may not easily notice.
So now we would see process of JPEG image compression. So as you can see in this diagram, the first step is to construct n cross n sub images. Then we would use some type of photo transform to compress the signal. Then we would use the content quantizer, and then we would use symbol encoder. Now let's understand what they are. So the source encoder's main job is to change the way information is presented in a signal so that the data is condensed into smaller set of values. This makes the signal easier to work with and takes up less space. It does this by using different mathematical transformations like the discrete cosine transform, discrete wavelet transform, and discrete Fourier transform to pick out and emphasize the most important parts of the signal while getting rid of the less important details. Essentially, it's like compressing the signal to focus on the most essential information. Now, what is quantization? So, quantization is a process that aims to reduce the number of bits needed to store transformed coefficients by making the values less precise. This can be done in two main ways. Scalar quantization. This means adjusting each transform coefficient individually to reduce the level of detail, therefore needing fewer bits to represent each value. Vector quantization. With VQ, instead of working on individual coefficients, a group of coefficients is adjusted together to achieve a similar reduction in required position. In simpler terms, if I say, quantization is like a rounding of numbers to make them simpler and easier to store, either one at a time or in groups. This helps save space and makes it more efficient to handle the data. Now, what is entropy encoding? So yeah, entropy encoding is a way to reduce redundancy in data by getting rid of repeated patterns of bits that show up after quantization. There are few common techniques used for this. Hoffman coding. This method uses shorter codes for more efficient frequent patterns of bits, reducing the overall amount of data needed to be stored the information. Arithmetic coding. It's a method that assigns a code to a group of symbols based on the probabilities of occurrence, which helps to compress the data. And run length encoding. This technique replaces repeated patterns of bits with a shorter representation of this pattern and the number of times it repeats. And at the last, Lampel-Ziv algorithm. This algorithm looks for repeated patterns in the data and replaces them with shorter representations, effectively reducing the size of data. So yeah, that was the process. Now let's see the working. So like after the compressed image is created, the decoder implements the inverse sequence of steps of encoder, which performs four relatively straightforward operations: sub-image decomposition, transformation, quantization, and coding. Or any or all of the transformation encoding steps can be adapted to local image content called adaptive transform coding, or fixed for all subimages called non-adaptive transform coding.
Now let's talk about discrete cosine transform. Discrete cosine transform is a mathematical technique which is used to convert image from spatial domain to frequency domain. Here is the mathematical representation for it. It transforms pixel data into the frequency coefficients by analyzing blocks of pixels and representing their brightness variations as different frequencies. It does this by applying a mathematical transform which is given as follows. You can see that fxy is the smallest spatial domain for a given pixels, and the alpha u and alpha v is the constant which is as per the requirement which is given in the down below, as its value is root 1 by n for u equals 0 and for root 2 by n for equals 1 to n. Since it is a cosine transform, so it creates an h over dft, that is discrete Fourier transform and discrete wavelet transform. Now we will see that how it is better than discrete wavelet transform and discrete Fourier transform. So in discrete Fourier transform, we see that data is represented in the form of sine and cosine functions in while capturing the information of frequency. And we know that in sine and cosine, the imaginary part and real part plays a significant role. So it makes a calculation a bit lengthy and complicated. So, and it has not DFT doesn't have spatial locality and can result in creating less efficient image compression after all the computations. In case of DWT, it computes in both frequency and spatial information, but its computation is far more difficult and complicated with respect to uh, the discrete cosine transform. So the preference is given to DCT as per the simplicity and the computational efficiency in many uh, computational expression.
Now let's talk about quantization and why we use this. So as we have seen that from DCT we get coefficient of 8 cross 8 matrix, as we can see here in this image. The image that is originally we have captured is made of one of these elements or in combination of these elements. But what is the contribution of all these elements? Will it be equal? No. Because if you see this white color, right? This white color can be represented by this first line. But if we see this boundary between white and blue, that can be represented with maybe second line, like that. So basically this total image is made up of one of these matrices or combination of these matrices. And what the DCT gave us is the coefficient that which are the matrices that are being used. Now we have to reduce that information further, because we can see that the image which is in last year, like 7 cross 7 or 8 cross 8 in the table, that will not be used in day-to-day life because it is a pixel, and that pixel has this many variation in detail. It must be a kind of noise only, right? So what is quantization? It is removing of high frequency data, which is useless density coefficient basically. So this is the quantization table, and this is the standard quantization table that represent quality of 50%. Now there are some questions, right? That what is f of UV quantization? This is given by the original coefficient that was given from DCT divided by the coefficient of quantization matrix, which is QUV. So f of uv new will be equal to original DCT coefficient divided by q of uv of this quantization matrix which are given below. Now here we see two quantization matrix. One is of luminescence and one is of chrominescence. But why it is difference? What is luminescence? What is chrominescence? So if you see, the human eye can perceive the brightness in much better way as compared to the colors. Can you see the variation between this color and this color? There might be some variation, but we cannot identify it. It might be that this part of cloth might be in sun for a longer time, so it might have faded, right? But if you can generally see the brightness, whether it something is dark, something is little brighter like that. So this to represent these two quantization matrices represent that only. First is of luminescence. You see, first entry is 16 and the last entry is 99. This part will come in the denominator of the above formula. So you can see the numerator will be reduced. So the number of bits required for encoding will be reduced. And the data which is transferred will be approximately same only because we have seen earlier that the image encoded by 8 cross 8, which is very much of high intensity and varies a lot, is almost a noise only and non-significant. And the chrominance part, you can see that a lot of entries are 99. They are 99 because they are not useful. We can perceive color in the same way. What is the difference between peach pink and peachy pink? There is none difference. Means it is negligible, right? So that is why in chrominance matrix we use a quantization of higher level so that we use a lesser entry because that will produce original color itself. And in the luminescence part, we are doing quantization of a large portion because that is more important part which our eyes perceive, which answers the question that why there is difference between these two quantization matrices. Now, how that is done? The first was that we have seen that 0 cross 0. You see, this is almost a constant. So if it is present in the image, it is almost like a DC component. Like in the signal, if something is 1 and it is continuously on, so it will be represented by 1 only. Like that, the first part is DC component. If some image like this 0 cross 0 is used to make the image from left to right in our current slide also. So that is used continuously. So it is like a DC component itself. So that is represented by the first entry of this quantization matrix. And after that, we follow a zigzag pattern. Now the question arises, why we follow this zigzag pattern? We can go in row-wise fashion, in column-wise fashion, in any manner. But why this zigzag pattern only? So we again come to this area. If we see this from 0 cross 0 to 0 cross 8, we see that it is varying and the frequency is changing, that how frequently something is varying. Same goes from 0 cross 0 to 8 cross 0. The frequency is varying. So if frequency is varying in one direction, that is x direction, it is represented through this direction. And if it is varying in y direction, it is represented through this. Now we are saying that the intensity continuously varies in both directions, so much so that it is affecting pixel itself. Do you know what is the possibility of seeing that detail? I don't think we can see it with human eye. You can see pixel. If you pixel peep, like if you come this close to your screen, then only you are going to see the pixel. And then after that, you will going to see the RGB palette from which that pixel is composed of, not this pattern. So it is basically useless detail that we are capturing because we cannot show it. So we have to reduce this data. And after reducing this data, our image size will reduce by quite a lot. So that is why you can see the lower right side of the matrix. All the entries are 99, 99, 99 and bigger entries. In luminescence also, the entries are getting bigger in the right side because that part of the information is not important since we can reconstruct almost original image from the upper left half of the triangle of the matrices that the quantization give. So that is why the entries are varying like this, and the first entry is 16 only, and that is the DC component which will give us the biggest value and it will represent the overall brightness and change of the image. So that is why the first entry is smallest. And now going into the zigzag manner, suppose the color is varying, okay, and 16, then 11, then 10, then 16, then 24. On this 24, the original image was turned from black to white. So that is important encoding. Then after that, it is white only. So there is no need to encode further image because the change was noticed then and there only. After that, it is minute detail which is varying a lot. That is noise itself, not the detail which was actually captured. So we move in the zigzag manner. Why? Because suppose one image is composed of 0 cross 0. Right. If 0 cross 0 is used and 0 cross 1 is used, what is the possibility that after 0 cross 1, this matrix 8 cross 8 is gonna be used? It is none, almost none. That is why we move in a zigzag manner, because in both direction, in x direction and y direction, the point where we move is the important part first, and after that comes the part which are less significant, lesser significant. So if we move in one way, so we will move from important detail to very negligible, non-significant detail at one direction. But if we move in zigzag manner, we go from relevance to non-relevance late, capturing the important information along the way also. So 0 cross 0 is encoded, 0 cross 1 is encoded, 1 cross 0 is encoded, 1 cross 1 is encoded. These 4 pixels will represent the general idea of the image by themselves also, but it might be pixelated. So that is why we include 1 comma 3, 3 comma 1 also in that area, but not the further part. We can remove that part. That is why we have to move in a zigzag manner. And suppose that some 0 came in our original image, that the intensity is 0. Now after that we need not encode any information, because from that point, no matter what the frequency is going to be, it is useless. That is why we move in a zigzag manner. And first part is the DC component. And as you can read this, we then serialize the final quantized data. That is the data that we got by dividing the quantization coefficient with the original DCT coefficient in a zigzag manner, and which, like, you move in a zigzag manner, so you are capturing the pixel detail. So you write 10011111, and after that continuously 0 will be there because they are encoding no information, right? So you write that all the points entries in the matrix in one line, and on to which Huffman coding is done, which will be explained by my roommate Divya. And now let's come to the final part. The quantization table that we have used, that can be varied. Suppose we want to do some granular information, right? We are seeing some microbacteria. So that small detail is also necessary. So if we want to compress that image, we do not want to lose 50% of the detail that we are going to lose from this quantization matrix. So custom quantization matrices can be used, and that can also be saved with the image themselves, which will be used by decoder to give back the original image. So this is all about the quantization. Thank you.
Now moving forward to the color specification. So the question arises, we can see the image. There is on the original image there is RGB to YCBR CR conversion. Why this is so? Why can't we use just the RGB system? And what is the need of color specification? So let's talk about it. Human eyes are more sensitive to brightness than colors. For this, JPG allocates more space for brightness information than color information. This is the reason primary RGB system combines luminance prominence attribute to create a visual output. But we need a luminance and prominence attribute separately, which affects in more efficient processing and transmission of color signals across various applications. So new YUV color is required to perform these roles where component Y, CB, CR are used for color image. Y represent luminance and CRCB combined represent luminance blue and red respectively. The lumen component represent brightness and the other two components represent color information. Now, why CBCR? Color space is better suited for image efficient compression because it keeps luminance information which is carried the most detail in only one channel. This conversion is simple or arithmetic operation which is perfectly reversible. Apart from, if there are any rounding error, we can see there is a matrix which is the conversion of YCBR to RGB. Moving forward to Hoffman coding. The process of Hoffman coding is applied to quantize GCT coefficients. These use Hoffman table defined by the application for compress an image, and then the same table is used for decompression. Hoffman tables are predefined and computed specifically for the given image during initialization prior to compression. The Hoffman coding collects unique symbols from the source image and calculate the probability for which each symbol and sort the symbols. Further, the lowest probability value to the highest probability value, the two symbols combine at a time to form a binary tree, where the shorter length will be more priority and the longer length will have the less priority. To obtain the Hoffman code for a particular symbol,
all zeros and one collected from the root to that particular node in the same order. Moving forward, a code tree is thus generated and the Hoffman code is obtained from the labeling of the code tree. Hoffman code's procedure is based on the two observations. More frequently occurred symbol will have shorter words code, and the symbol that occurs less frequently. The two symbols that occur least frequently will have the same length. These are the two common procedure and observation which we see in the Hoffman code. The Hoffman code is designed by the merging of the lowest probable symbols, and this process is repeated until only two probabilities of the compound symbol are left. Thus, a code tree is generated. Hoffman procedure is code each reduced forces starting from the smallest source and working back to its original source. So we use binary digits 0 and 1. Each source symbol is mapped to a fixed sequence of code symbols. This is the formula for finding the average code length of the Hoffman by Hoffman. L is equal to minus log q log 2 base pq. At first we have as much as compressor does as a probability distribution. The compressor made a code table. The decompressor do not use the same method though. Instead, using the whole Hoffman binary tree of course a pointer to the root to the recursion process, in our implementation, we make the tree as usual. We'll navigate the tree by using the pointers to the children that each node has. This process is done by a recursive function, which accepts as a parameter a pointer to the current node and return the symbol. In a JPEG, there are separate Hoffman tables for direct current coefficients and alternating current coefficients, as current coefficients represent average color value for the block, whereas AC coefficient represent a deviation of this average. Hoffman coding in JPEG effectively reduce the number of bits needed to represent the quantized DCT coefficient, contributing the overall compression of the image. Now, we can see there are two tables. One is Hoffman source reduction, where probability is distributed from the highest to the lowest from going up to down. And there is a second table in which Hoffman code assignment procedure is done, where more probable code have lesser code. This is the formula which we have used, which we have seen previous here, and use to calculate the average length by the Hoffman coding. And the entropy of the source is 2.14 bits per symbol, and the resultant Hoffman coding efficiency is 0.937. Thank you.
Now let's move to the final step. That is, after we have compressed the image, how we will retrieve the original image that we have originally captured. So that is through decompression. As we can see in this model, the compressed image first looks the symbol decoder. Symbol decoder is the table that we have obtained in Huffman coding. So from there, we will obtain the Huffman codes of the table and we will fill the image in the backtracking manner. Now we have come to the part where the zigzag pattern was followed in the quantization table. Now that zigzag pattern will be filled again from the symbol decoder, and that zeros will be converted and filled accordingly in the matrix only, because the matrix is what the image was in the original format, right? Now after that, we will see which DCT block was used, like what was the contribution of each block to make that particular image. And if we convert from discrete to like cosine transform itself, it will include like what were the cosine values used from the 8 cosine values which was used to make that particular block. So we will apply inverse DCT on the quantization matrices that we have obtained from the symbol decoder. Now, from that, the values which we have obtained from the inverse discrete cosine transform is only a sub-image. Now we have to obtain it for the whole image and combine that whole image. So that is what the last step shows in the diagram, that merge that n% sub-image, and after merging all of it, we will get the decompressed image, which was our original image itself, and now it is represented in our device from a smaller size. Now let's move to the final part of the video. That is the results of all the things that we have done from beginning till now. So we have seen that we are taking an original image and its size is big and we want to compress the image. And for that we use JPEG compression method. We have explained what is JPEG compression method, and this is the result of the JPEG compression. This was the original image and this was the JPEG compressed image. Below you can see some parameters, that is compression ratio, PSNR value and MSE value. These are the results that we will obtain from running the code in pie chart here. So if you will run this code of analysis of results, you will get this. Don't worry, we will be providing the GitHub repo link of this codes and all. And for running the optimizer image, that is to get the compressed image, you have to run this Python code. And here the image address should be given. And if you will run this, it will, for our image, it's gonna take around 4.6 minutes. So this was the dimension of original image 3456 cross 4608, and it was 3 channel like RGB, and this was the total number of pixel count. And now it will take around 1.5 minutes to do proper encoding and Huffman and stuff, which is done through this code here, and it is also provided to you. And these are the utils library, which is using zigzag points and all that we have taught in quantization. So this is used to convert the original image that we get from DCT to a serial line on which Huffman code is applied. And this is the code of analysis of result, which is going to give you these parameters. So hope you have enjoyed this video, and you can try this all by yourself also. And what are these values will be explained by Aditya. Thank you.
Next topic, which is we are going to discuss, is analysis of result. And in analysis of result, one perspective can be compression ratio, which refers to the size of the proportional reduction in the size of the image after compression to its original image. As we can see in the formula, n original by n compress. That n original refers to the original size of the image, whereas n compress refers to the compressed size of the image. Now, again, another perspective is distortion measure, in which we will look after mean square error and signal to noise ratio. Mean square error is a measure of square difference between the corresponding pixels values of the original and compressed image, which can be seen in the formula that Fij is the restored image and Fij cap is the original image. And when we are restoring, we measure the values of each and every pixels, and we take average out of it. Then the signal to noise ratio. It is used to quantify the quality of image after compression by comparing the strength of signals to the level of noise introduced after compression and subsequent decompression. The peak signal to noise ratio is given by the formula 10 log 255 squares of mean square error. The 255 square signifies that it is an 8 cross 8 image which is there at present in the JPEG compression.
So summarizing what we have seen in this video through conclusion, JPEG compression is a sophisticated process aimed to significantly reducing image file size while maintaining a acceptable visual quality. The algorithm begins with a color space conversion, transforming the image from RGB to YCBCR and separating luminance and chrominance information. Downsampling of chrominance channel follow leveraging the human eye's decreased sensitivity to color details. The image is divided into 8 cross 8 pixel block from efficient processing. The application of the discrete cosine transformation facilitates a frequency-based representation of the image, enabling effective compression. Subsequent quantization strategically discard high-frequency data, especially in less area perceptible to human eyes. The quantized data is then subjected to entropy encoding through a technique like run-length encoding and Hoffman encoding, further reducing the file size without sacrificing critical visual information. JPEG decoding, performed by a viewer, involves the reverse application of these steps: Hoffman decoding, RLE reconstruction, and inverse quantization. Reconstruct the compressed data. The chrominance channel are upscaled and the color space is reverted from YCB-CR to RGB. The result is the images closely resemble the original, striking a balance between file size reduction and visual fidelity. In summary, the JPEG compression achieves efficient image compression through a series of well-designed steps, making it widely adopted standard for balancing storage efficiency and image quality in various acceptance applications.